Hi, JP. Cash, how are you?
Hi, David. Good morning.
Good morning, everyone.
Morning. Get started in a bit. Hey, Kash.
Hey, JP, how are you?
I am good. Thank you. Thanks for sending all the slides last week.
Yeah, I'm trying to see if we can get some help from some people. Right? It's like pulling teeth, as you know, right? So
Yeah, perfectly understand. But it's a good compilation. We had some questions. We went over it, and so maybe you can this week we can go through it and clarify
sure.
some of the points and where we stand and what's the next steps are.
Okay.
Overall, it looks good.
Okay, let me.
Yeah. Jawad won't be here today. He's on vacation this week. And give me a minute or so. Then I'll be in a meeting room and then we can get started. Yeah, I see Mark also joined. Hi, Mark. Good morning. So, Tosh, we can get started.
Yep, hello.
Yeah, we can get started, Tosh, if you can hear me.
I guess I was on mute. Okay, let me just share those the slides I sent over.
Okay.
Um, okay, so I'm sharing, I think.
Yes, you are.
Okay, we'll start. So this is come from, as you all know, every time we talk about chiplets, somebody says, "Hey, we really want to do a plug fest," right? So and it doesn't work, right? So there's chiplets, and they're like very, you have to be very close to some of the thing. You have to have potentially a substrate or something. So it really gets difficult. So that was um, just a backgrounder. I mean, you all sort of know this, right? But just to address it for other people that I've shared this with, which is like, hey, you can't just go around and plug your chiplet in. I mean, it doesn't, it unfortunately won't work. And so I think you've all talked about it, right, JP? I mean, the last time you were trying to do something, and then the money was also tight, and getting the substrates done is expensive. The vendors, as you know, are expensive, and then I think we've also addressed this pitch issue. As everybody knows, the pitch that is going to be available is changing dramatically, right? It's a moving target. There's a lot of technology happening. And if you have to do a new substrate each time, you're going to do some sort of let's say a substrate test. That not only has big expense, it also has lead times and so on, which really gets really problematic, right? So as I think some of you at least know, we're working on our own PHY, which is sort of the version of that is the Bowflexi that we're talking here, and we're sort of internally calling it UCIe Lite, without getting too much into what we're doing, but we are doing a PHY, right? And so at least from my standpoint, it would be great if we can at least think through interoperability for that, because I think that our PHY is meant to be more generic. And so we've already had discussions with QuickLogic, right, which is an FPGA vendor, and that's public, where they've expressed interest and are interested and are planning on potentially an FPGA chiplet, right? And so what we wanted to do was to propose something like, you have Bow and then you have UCIe, whether this is regular Bow or Bow Flexi or what, if we're doing it, we're definitely going to have Bow Flexi on our test chip, and we will have
Sorry,
just so
Kash,
you
quick
know.
question.
Yeah.
So is Bowflexi and UCA Lite that you have are two different files or the same file?
It's the same PHY, but configured differently, one for UCIe, one for a bunch of wires.
I see. Okay, got it. Okay.
Right. But it is not a standard UCIe PHY or a standard. It will meet the standard of Bowflexi, right, which is still an ongoing development, right? So where whatever process node we end up with, we can talk about that. But if there is somebody else with a UCIe, it would make sense to throw that on the same die in reality, right? So we're not saying this is just our chip. If we are going to tape something out, we would be open to sharing that MPW, or our interest in sharing that MPW regardless. Okay. So after a number of conversations, 22FDX seemed like a reasonable process, because there are US government people wanting to build something in the US, right? So the thought was maybe we could leverage that, right? If I don't know whether we can get interest from them, but there should be some interest there. This is a process that we and QuickLogic and others do get interest from people. Okay. And so we're interested in this as a platform, because this is a good IoT platform. It's also a platform that may have interest in the US government. So
sorry,
yeah.
Kash again. So
That's
22FDX, 22FDX is equivalent of 22 nanometer TSMC.
It's a little different, but yes, effectively yes.
I see. Okay.
They're the same level. They're targeting. I think that the GF process is fully depleted, so it's got some power and advantages, but the key thing is that it'll be manufactured in the US, right? So
I see. Okay.
and there is sort of a broader and it is one of the few process nodes that the government wants, which is also used heavily in commercial and automotive and a broad range of applications, right? So the GF22 is a very popular process node. Just as background. And then there is also a GF12 nanometer, which is a FinFET type of process, right? So so if somebody wanted to do that and wanted to support that, we would be interested in supporting that as well. But that's more money, just so as you know, right? So 12 nanometer is inherently more money, so 22 is less so. But that's an item of discussion, right? So I think what we want to do is see if there's some community effort to enable something like this. And then the idea was that for the initial testing, we could just put them back to back, right? So very similar to what you were doing, except what you were doing was back to back was two chips from different vendors. In this case, this would be the same chip, because if if nobody else has one, at least we can test against that and have a calibration point. And the idea behind a memory chiplet is you really need to load something into a bunch of memory and then sort of blast it at reasonable speeds into these interfaces, right? So you can test them. And the FPGA is attractive because you can change the patterns that you send out. You could do a number of things to make the testing easier, right? So and the FPGA chiplet can have memory and well obviously we'll have some memory and block memory, etc. and set it in here. So that was
Prakash, what is speed you're thinking about for the interface?
What is what?
What is the speed that you're thinking about for this interface?
Well, it depends on what. If there's an external UCIe, then it could go up to 16 gig, right? The Flexi is targeting up to 4 gig or 5 gig because it's an SDR. It's meant for very low power, sort of mass market kind of applications. So it's lower power. It's easier to promulgate. So it's ideal for people building edge type devices, right? So that's one of the real markets for Flexi is somebody says either UCI or regular UCI or regular Bow gives me a very large die phi, right? And it's not suitable for high volume. So that's one of the applications for it.
I see. So somewhere between 4 to 16 gigabit is your target.
Well, 4 gig with the Flexi for UCIe, then I think it would, that typically goes up to 16 gig. But we're hoping that I mean, I don't know if somebody exists at the moment or when they come up in the future, you could put the one on. And I'll come to how you can handle or want to work with other chiplets as they come along, right? But so this was just, hey, can we prove this? Can we prove this with some packaging technology that is viable, right? Which doesn't require a substrate each time, right? That was the other part of the whole cost. And obviously you can have a third-party chiplet in a different technology, right? Once this is proven, right? So and so this UCIe or this Bow or whatever exists can talk to a specific chiplet. And I think the idea of the bridge chiplet is as people change, because the specs are changing, the speeds are changing, even if this is 16, somebody says, I want to go 32, I want to go 64, you can have multiple people. So it's very expensive to just keep redoing this, but it is easy, it's much easier, not easy, to build a bridge chiplet, right? So you can then use a very small area in an MPW and it becomes much easier. And now you could actually do testing and validation. And if there's a new UCIe 2 standard, for example, that this is, then this bridge chiplet could have UCIe 2 on this side and a regular UCIe on this side, right? And then you can still run the traffic. So that's basically the idea. That the reality is that the standards are changing, the pitches are changing, right? So it's if you build something, there may be no market for it after a year or two, right? Because the packaging is changing and the standards are changing. So I think that you want something that is friendly to a bridge chiplet, because it's not just the die-to-die standard changing, there's also the pitches are evolving, and they're evolving kind of rapidly. And then this was kind of the status.
Sorry,
yeah, sure.
One more question if we go back.
Yep.
So what is the idea of memory chiplet? What is the interface you're thinking about?
It would
chiplet?
be it would be some sort of a die-to-die, either Bow or Flexi or UCIe, whatever, right? So we're having some discussions with some memory people that might be willing to help, right? So one for example, partner we're talking to does MRAM. So MRAM has very high speed access. they would like to validate, that out. And there are obviously other memory vendors or different types of memory, ReRAM, there may be some other non-volatile, there may be some other SRAM somebody wants to check out. So this is meant to be sort of, again, a platform where you could try different memory types, right?
Mm.
And here's more for a logic type. So those are the two kind of applications here.
I see. So
And
you different types of memory interfaces, you abstracted a common BOW or UC type of interfaces. Is it?
So for example, there is a Bow memory coming out,
Mhm.
or talk of that, right? So the folks from Ilion are proposing that. And I know a gentleman from Infineon has come up with some ideas. So I think there will be some interfaces that are optimized for memory use.
I see. So, Akash, this is just a general question. Like, for instance, we need a very high-speed memory like HBM. The D2D interface makes sense
Yeah.
because it's a high bandwidth and you need a D2D. But
Mhm.
if you have a MRAM type of interface and that interface itself is very small, right? Do you think
That's not
we would
true.
need
That's not true. There are
okay.
people wanting to run wide MRAM interfaces to store weights and things like that in the non-volatile memory, for example.
I see. So you also have high-speed interface to these emerging memories.
Yeah, I think there's interest in that for sure. And leveraging die-to-die type interfaces for power, particularly for edge type devices, yes.
Interesting. Okay.
Yeah, it's a different world. People are exploring every kind of technology and seeing how it can be applied to AI. There's no all the rules are being redrawn.
Yeah, it's
Mhm.
not just HBM and data center, right? There's another world out there, like in drones and cars and robotics,
Okay.
right?
Okay.
And HBM may be slightly expensive for that or overkill.
Mm. Yeah, interesting.
Yeah, and so at least trying to see what we can leverage with people we're talking to right now is obviously, QuickLogic has already got a silicon proven 22 FDX, and they've said that they would be willing to provide that, or consider providing that as part of a Golden Die project. And obviously, we are interested in having our PHY if and when we do a test chip in 22. Frankly, where the initial test chip that we're doing is not in 22 FDX, we're going with TSMC. Okay. But we see enough interest in 22 where if there was an effort, we would be willing to support 22 FDX. And then we are talking to some people who have interest in high speed memory, whether you're doing a processor, like a processor cache type of application or whatever, right? Whatever. And as well as different novel non-volatile high-speed access type of thing. So the one reason to try to get why I thought 22 might be a good platform is because of the US. There is OCP is really data center oriented, as we all know, but there is a lot of US government interest. So the hope is that maybe they would be interested in interoperability, right? And supporting chiplets in a broad range of nodes. I think that they've already sort of expressed that. So I think that is maybe an avenue to get some support and funding. Maybe they could spring for an MPW run or convince GF to do something, right? And GF is an OCP member. I don't have a GF contact, so I don't know who does, but obviously somebody at OCP does if they're a member, right? So that was basically the idea. And then Deca is a US company that has the ability to not require an interposer. So it does seem like their technology would be very good for mixing flexible pitch. So for example, if this device was on this side was, let's say, 55 micron pitch or 45 micron pitch, and this more advanced device was in 25 micron pitch, they instead of needing a bridge chiplet or an EMIB type of silicon bridge, they have the technology to actually route that in the RDL layers, because they use adaptive patterning, right? So they actually use lasers to do so they don't need a mask. So they have some unique technology that would make this viable, right? So it would potentially have the opportunity to reduce some of the risks and development cost of doing specific interposers and stuff to do this work, right? So I think they would be potentially a good partner.
Oh, so gosh, this is interesting that they don't need the mask, is it, for this process that to develop the advanced packages?
Yes, I mean, their technology is going. Okay, they have one technology called M1, which is already in high volume at people like ASE. It's been used on iPhones and stuff like that. And that I think goes to 45 or 55 micron pitch. I'm not familiar with M1. They have an M2 which will go down to 20 micron pitch. Okay, and that is going into the Arizona hub in Arizona, and it's going into some other commercial uses. And so basically they can they use the lasers to they can even make change the routing, or whatever. Even if the wire is there, they can adapt to the errors that exist when you actually physically place devices, right? The die don't align exactly 100%, right? So whether you have an interposer or not, right? So they have some technology, they call it adaptive patterning, and it's all done via laser. Or
I see. It's like
thousands of lasers. Yeah, it's very exotic technology, but apparently it works, and it's being used in high volume.
Interesting. It's some sort of 3D printing type of technology.
It's what?
Some sort of 3D printing.
Well, it is 3D in the fact that it's doing a layer, right? So it's basically runs in the fab, right? So they're still processing RDL. So it's called advanced package. So they're a public company. Well, I don't know, they're not a public company, but their technology is public. They are part of some of the U.S. government programs, so they may be a pathway to get some DIB support. I'm just throwing things at the wall that we thought of when we were brainstorming, and we would then need to talk to through them or through GF or to the Arizona hub. And I think also there's a packaging facility going up in Florida for the US government that will use this technology that's for commercial and military use. And I think IBM I think it's public, is also putting this technology into their Canadian facility, which is a high volume commercial facility that's commercial and military. So yeah, so that was my my sort of update as of a week or so ago, and I continue to talk to a few people on this. But what we really need is to expand this, right? Because we don't have much reach, even in our little group. We don't have much reach, right? So I think if we could get either something from the government, not necessarily money, but just a push to say, hey, or GF to say, hey, here's and GF has a sort of a free MPW program if they buy into it, right? So like a 3x3 millimeter kind of thing. That would go a long way, I think, to get other vendors to say, hey, maybe I'll put my PHY on here, or I'll modify my PHY to to go on this node or whatever. So I think so. Anyway, so those were my comments, and because I think that if we can actually get some buy-in from some people, I know that in the business group, the study that they had done, the lack of interoperability was the number one issue, right? And so how do you do that with a reasonable cost and make it sort of open? And if somebody else comes along with let's say a different chip that could also become a golden, or we could, for example, be a golden die for Flexi and UCI Lite or some other version. As somebody else does an MPW, if they're willing to make it open, that could be a golden die. Let's say Elion does something, right? Or Blue Cheetah does something, and they as they prototype something. I mean, it could be in some much more advanced process, but the die could, again, it can fit into a platform, and you can say, okay, we'll use this one as a golden die for this type of broad ecosystems, right? So I think that's kind of the thought process, not tie it into any specific vendors, but just make it as flexible as possible.
Okay. So Kakash, is that the last slide? I thought you had more slides.
Did I? I can't remember. I think that was. Oh,
Oh yeah.
yeah.
No, I think that's
I've already
yeah.
talked. Yeah, I think I already talked about this, right? With bridging, you can build something that's very small and do stuff in advanced nodes. And everybody who does test chips has small test chips in advanced nodes, right? Because the costs are so darn high. And you could even also reach out to, I mean, I don't really have context there. Like Intel is definitely looking to push their, 18A. And so in fact, QuickLogic guys have actually delivered an FPGA block. I mean, they were at the announcement earlier this week, right? At the Intel Foundry event. And so Intel is doing, and people are doing test chips on that 18A. That also would be an interesting to have a golden die in that technology, right? And maybe they could, if they were interested, then they could, they could certainly help us. And I know that one of the Intel Foundry people does attend some of the calls, so we could maybe reach out to him.
So what's the proposal encompass, Akash? Is it like golden die plus package associated with that, along with a third-party chiplet?
Yeah, hold on. Sorry, I didn't understand the question.
No, what is the proposal actually encompass? What does it consist of? Golden die, package, and the bring up of that, or what is what?
Well, I'm just putting out my ideas for, as I promised to do, of is there a way to even talk about a golden die? And I'm looking for feedback, and I'm not making a formal proposal, right? I think that's something for the group to think through and discuss. And then we can socialize with other team members, right? Or other groups within OCP. To see if there is a possibility of supporting something like this.
I see.
I'm not proposing doing a white paper or anything, right? It's just like, hey, I think we need to go out and socialize this as hey, would there be interest in something like this? And again, I don't know what OCP's capability is, I mean, there are a lot of members that they can reach, right? And we also could even reach out to the UCIe guys, right? So that's maybe Anu or you know the other people.
Right.
So yeah, so that's what I'm hoping is that we can socialize this and get feedback from people that may be involved with the DIB, maybe involved with some of the foundries, and you know, right now there is nothing even for UCIe or I mean, I think they tried and then they've changed direction. We never tried, right? So at least I think that for Flexi, I think that you know your chip will do something along these lines. So we're trying to leverage our thinking because having an FPGA does allow you to do some testing, right? So you can you're kind of flexible, you're not fixed. And so once we tape out an FPGA chiplet, that kind of becomes a I would say something it makes life easier rather than have to go off chip to an FPGA, right? You have an FPGA chiplet right there that can send data with you know immediately to a chiplet or a brick chiplet next door, right? And then that can blast the data at much higher speeds if necessary as technology moves.
Right. And what a target application that you have in mind is kind of IoT type of applications or defense type of applications, right? For this, at least the concept that you are laying out. Do you think the companies who are working on this would be interested because it's their interest to actually have something interoperable IPs available? Correct.
Well, everybody says that they're interested, right? And you know, even you know, if you look at people doing edge devices, they're not they tend to be the smaller companies right now, right? And then the bigger companies are like the big microcontroller companies who are still evaluating whether chiplets make sense. But you know, NXP, Analog Devices are all people who participate in our calls and stuff like that, right? So they have ongoing programs. NXP, I know the Infineon guy has attended some of the memory meetings. So yeah, no, I think that there should be. I don't have anybody that says they don't want to encourage interoperability. But the challenge is getting people to actually do something, right? So I think that's just a fact.
I see. I mean, one thing I would suggest, Kash, is actually if you put together a few applications, right, that you have in mind, let's say not as a golden chiplet, but the kind of markets that you're thinking about, these are the kind of things you can do. Let's say a CPU talking to let's say a memory, a CPU talking to an accelerator, or something like this, that showcases the concept, and then say these are the areas where you want to demonstrate the interoperability, right, or develop the golden die for. I think we can actually probably scout more adopters or evangelize it that way.
Yeah, so I'm open to other, you know, whatever suggestions exist. Yeah, so like I said, I think that you know there are some pretty clear areas, right? And in terms of the data center, it's probably less interest because that's really driven by the NVIDIAs and AMDs, right? And AMD is part of, I mean, AMD is part of our, you know, I mean, they're now saying they're going to open up and develop some open chiplets, but then you give them your chiplet and then they'll integrate it, kind of thing, right? So I'm not sure how that's going to go. That was essentially what they're proposing. but there are other, like Alpha Wave is one that at least has open chiplets. I mean, on the open chiplet economy, there's a whole bunch of people that have listed their chiplets that they want to be able to sell to other people, right? So that's the whole premise of the open chiplet economy. As I understand the open chiplet economy, right? That's the theoretical target is I have a chiplet and I want it to talk to somebody else's chiplet.
I see.
Well, I mean, is that a surprise? Or do you think that's not why we're here?
No, I'm not.
Because the whole point of having the open chiplet economy means
Correct.
it's open, right?
Absolutely, yeah. That was the very first premise, right? The BOW and openness.
I apologize.
Okay.
We have cleaners in the house and there's vacuums going all over the place. So
No worries.
yeah.
So quickly, Akash, what is the next step in your mind?
I think I'm looking for feedback.
Mhm. Okay. I think we should also look for, let's say, another partner who can actually come on board, who can really demonstrate the interoperability. Right, then it becomes much more stronger.
We need multiple partners, right? From a fab partner to other IP partners and so on. If there's no one else, we're way too small to do this, right?
Right. Mark, would Blue Cheetah be interested in any of this?
Yeah, it's some level, yes. I'm still talking with them on a few things.
I see. Yeah, if we could take this proposal and brainstorm, and if you have any feedback, that'd be great.
Yeah, let me try and do that.
Yeah.
Yeah, we'll probably bring it up at the BOW-FI meeting when I get a chance, right? Because I've missed the last few because I've been kind of busy and traveling. So I'll definitely get Elad's. I don't think Elad will go for it because he's got different things in mind, but at least we'll get that, and then maybe we can also yeah, I don't know who at OCP to try and talk to, right? Because on the one hand, there's this messaging, we're building an open chiplet economy. And you're probably getting my frustration is, yeah, there's all the slideware, but then, okay, how are we actually enabling it, right?
Yeah. And just to come back to sorry, I've got construction going on in my house, but just to come back to if you have a direct line to Elad, that probably will be more effective speaking to him if you speak to him directly than if I do. So if that's convenient for you to do that, that would be better.
Yeah, I can do that. No worries.
Okay. David, anything from your side? Did we lose David?
No, I'm here. Sorry, I was on mute. No, not really.
Okay.
Yeah, this looks very interesting.
Okay. Yeah, I don't know. So, David, last time you proposed something with you were developing a chiplets with Georgia Tech, Fab Technology. Do you think any of them, anything what Kash is presenting today, resonate with that technology from Georgia Tech?
So yeah, I promised I'll talk to them, right? I didn't. I just totally escaped my mind.
Yeah, no worries.
Let me see what their thought is on
Mhm.
this, and see if they might be interested in doing something.
Okay. Okay. And you said you'll also have the student present to us about the technology in one of the Friday meetings, correct?
Yes, either 16th on the or the 23rd, depending on what the availability of time is at the OCP meeting. I just
I
sent this
see.
morning a note to Jawad and a note to schedule for either 2 weeks from now, 2 or 3 weeks from now.
I see. Okay. Sounds very good. I'm looking forward to that.
Yeah.
Okay. I think we don't have any other agenda. If nothing else, we can close the call and then we can circle back with Anu and then see what the next steps could be. And Akash, by the way, I'm just curious that did you also present this to the wider audience in the Friday 8 a.m. calls?
No, not yet, because I think right now we were just within the POC group, and then let's get, I think it would be helpful to have some outreach to some other people, and then it would be a stronger proposal if, like, I know Georgia Tech has something going on, and I mean Jawad may know of some other stuff going on. I mean, I don't know, right? So let's or at least somebody talk to Cliff or somebody, or Anu talk to GF and get their feedback, right? So I think if we get a foundry to say, hey, we will support this and do a free run or a free shuttle or something, put your ideas together, that would get a lot more interest, right? And then people can say, aha, I can take advantage of this, and maybe we could build 4 or 5 little test chips. So I don't know, right? So I think that would be much better than, and much more powerful if we can do it.
Yeah, I agree with that. And I would also encourage if you could also establish that market need for that strongly, right? So then it kind of pulls people in. Okay. Okay. Thank you, Gush. Thanks for the talk. And thank you all for joining. Let's catch up next time.
Yep. Thanks.
Yeah. Bye.
doable for having the two backside RDL. There's nowhere to go for the two backside RDL. That's why I think right now that is a more like a hot topic with the ASC. Because ASC point of view, there is a concern for the PI denomination inside the two RDL facility. So they is treated more like a 150 micrometer bumpage, okay, C4. But now I'm saying the 130 because I don't want to give a too large number. Then we have a problem for microphone to C4 routing, right? Yeah. So that to me is that all of our loud will be checked first. And the one is the louder. Yeah. No, so question is, are you expecting?
I'll get check.
That's it. Okay. Because if I continue again, this is not the one guy made the one. Basically, the micro bumpage, let's say 36. Okay, that's stable. Okay, and the C4 pitch. I'm open for talking about mixed bumpage, mixed C4. I'm okay. But in the 110, it looks like ASC has a challenge for 110 micrometer C4 based on the two backside RDL. Looks like they're not going to say, oh, I'll take it. No, I looks like they don't.
Can they do 120?
They didn't say anything yet. Even they don't, we didn't say anything about the real louding, how the louding looks like. And then once we show them.
No, let's do one thing. That I mean, your sweet spot is 139 microns,
Yes,
right?
That's my
Okay, so we'll evaluate 130 micron single layer RTL while you continue to look at 2-layer RTL as a backup, right? Because we need some backup option.
Yes.
So if that works, that single layer RTL 130 or 110 microns works. We don't have to do anything else.
Yes.
Right, but we in case we have trouble, then we'll come back to you for the 2-layer RTL.
That's right.
Yeah.
So that's why I want to see the trial for 130, 1 layer or 2 layer. How much I can help to the 2 layer RDA based on 130 or something. Then I can come back to convince the ASC say, hey guys, we're in trouble for routing from microbump to C4, and then this is the must to have. I'm already keep saying must to have 2 layer RDA. Okay, but they didn't come back anything yet because they're scared. And when they produce it, then they have a PI lamination crack or something under the C4 area. There's nowhere to go. That's why they're scared to yes.
No, true. We have to balance each other then. So Firefox, you're going to test the 2-layer RTL theory, right? But develop technology.
Yeah.
Okay.
So I didn't get this. So option number 1 is 130 micron C4.
No. 110 micron single layer RTL. That's our target. That's
so
our
you're
first
starting
option.
with 110 micron.
Okay, exactly.
And one BSRTL.
One backside RTL.
Okay, and then option 2 is if this doesn't work.
Yeah. Then you will have
130.
130 micron, the 2-layer RTL.
No, 1 layer.
No, 2-layer. If you give 130, it'll be 2-layer RTL.
Why?
Because 2-layer RTL is what gives effective power delivery. They're thicker
Yeah.
planes, right? Effective power delivery.
Yeah.
Okay.
So we may be able to do 130 micron 2-layer RTL. We probably may come back to it. So
the
right
very bottom line is ASC promotion material. They said 2 layer. Somehow we decide to use only 1 RDA. Okay, if we decide to use a 2-layer RDA from the beginning, then we have a good starting point. Since we reduce it from 2 to 1 without saying bumpage.
You mean the Pavehawk test chip?
No. ASC promotion, general promotion material. They are silicon interposer can support the two.
Correct. Correct. Even TSMC supports 2-layer
Yes.
RDL, right?
But,
Everybody
but with
supports.
the nature of our pitch,
Yeah.
now we mention about 110, then we end up with 1 layer. If we say 110 for 2-layer, 130 2-layer, that is a talking point with the AEC.
Okay. No, 132 layer is also workable. 2-layer RDL, 130 micron is a workable solution. We'll keep that as well.
Okay, yeah.
Right. If let's keep, and then we'll also try single-layer RDL.
Yeah.
And we require some evaluation. Right.
Yeah.
Let's say if a single-layer RDL does not work, we can actually go back 130 micron 2-layer RDL.
Yeah. Yeah. Okay.
Yeah.
That's
Yeah, so basically these things, right? So APM requires the bump map by end of June.
Okay, APM actually the DRAM. This actually affects the DRAM, right? Not
Yeah.
really our die.
Correct. But they need
But
the
end of June, is it?
End of June. Yeah.
Yeah.
So do we have enough time for evaluations and like, or do we want
It's
to take a
about 2
more
months now,
conservative
right? June.
approach?
Okay.
So do we have enough
No, we
time
need to
for,
actually prototype quickly and then verify this, whatever we talked about, right? Krishna, do you have any thoughts?
Look, so there are two problems. One is like what we discussed yesterday, right? That
Hmm.
portion we can do from
Hmm.
our side.
Hmm.
And that's what I was mentioning before you joined about, I'm going to see what kind of collaterals are actually available today and what we need so that we can quickly at least gather that information, right? And
Hmm.
start doing that.
Hmm.
But with regards to the original drawing,
Hmm.
I actually don't know how to, who's going to be, are we going to?
No. Once if you have that, Krishna, once the current the consumer is what is most important. The logic die, what you're doing, right? And then once you have that model, then we can. It's very easy to attach the 2-layer RDL, the power delivery, and all that, right? Because that's only a small segment in the interposer.
No, but the two-level RDL, is it going to be done more at a kind of a platform level simulation, or is it still going to be like just a die level check that we are going to be doing?
It will be another layer in your die, and then that will get added. Think of that as actually a very wide AP layer that you're attaching.
No, sure. But okay, we'll have to first see whether it's. I think on paper it is doable, right? It's just adding more models there to it. But is it?
We'll find a way because my AP memory has done in PayHawk. It's been done and simulated, right? We can take advantage of that, and then we can find out.
Yeah, sure.
Yeah. So the only thing is the time is a question. So for logic die portion alone, Krishna, how long do you think would it take for logic die? I understand the variability in the interposer part.
Yeah. Like yesterday, right? We were talking with Richard and I did talk after that. So one of the things is we do have the grid already prepared for the logic die, right? With the baseline till metal 15. Now we'll have to create this model wherein we add the micro bumps to the logic die in the appropriate location and stitch it up. And that one, if we have the macros, it can be done quickly. And that is the check that I'm going to do to see what kind of left we already have available. And then
Okay, let's say this, Krishna, that whole analysis, let's take, because we need to see also the routability. Arun, you mentioned last time, that a lot of tracks going through it. We also have to analyze that case as well. And let's say about 6 weeks for that, right? For the whole analysis, Krishna, what you're doing, right? Another 4 weeks for the interposer.
No, but then we have a bump map to start with and then work it out.
Yeah, we'll get a proposal. What Krishna and I discussed is we'll get a proposal from AP memory, like similar to what they gave for PayHawk 1. We'll have the first proposal from them. We'll use that as a starting point, and then we can actually verify if that works. If not, how to tweak it. So we have to start with the starting point. That is the proposal from them, and already Vishal has laid out that micro bumps as well, right? That we already have a plan in place.
So you're getting an initial bump map from APM?
Correct. Because because DRAM die. So most of it is actually is figured out, and Vishal has done the routing as well on the logic die with a bump map, right? We can use it as a starting point. And only thing is we need to actually work a bit more on the L shape versus the H shape, the 11 shape, right?
That so that's something we'll have to work with AP memory to put those bumps in place. So we can get an Excel view of that bump map as a starting point. It could be a rough approximate starting point. And then when Krishna starts modeling it, we can analyze where the bottlenecks are for all conditions, including the signal path. And then we can finalize where needs to be or what needs to be done, whether 2-layer RDL or 1-layer RDL, and how to deliver power to it.
Yeah, I like basically.
Who owned this? Is it Krishnan? Is it you that who own this? Or?
Yeah, so I can.
Yeah.
Okay. Okay. And the dependencies that you have from APM, you're going to drive that, or who's driving that?
Ganesh has those meetings, right? We can use Ganesh's meeting to actually get that information.
Okay.
Yeah, no, I'll remind Girish today.
And also the other thing, just to add to what JP said, right? This analysis is going to be a two-pronged approach, right? One is the bump to die, and then one is C4 to the pump, micro bump. So we are going to split it that way. So at least some of the analysis can happen independently. The final stitching is something we have to figure out, but the two of them separately can be tested out is what I'm thinking. That's what we were talking about yesterday.
Right. Yeah, that's the best way to do it. Right.
Where is the C4 going to be?
On the DRAM interposer.
So what we'll do is the logic drive will assume we are connecting to the micro bump. The micro bump locations will place properly for the power, and we'll do that analysis based on the default TSMC grid as well as any other grid that we use. And we should be able to see the number of tracks available, etc., right, based on those ones, at least on the logic drive. Then the second check is going to be a model that actually builds only the C4 to the micro bump in the DRAM drive, right, with the TSPs.
Do we not need to do both together from C4 because there'll be some LC on the C4 to micro bump also, right?
No, what we're saying is, Ganesh, if you want to do C4 to the logic drive completely in one model, right? It won't be doable initially because we don't know what is there, what is not there, how to model the C4. First, we'll have to assume that ideally, yes, what you're right. We have to stitch the two of them together, but we will have enough time for that because that's going to be the last portion. If we start off with that as the starting point, it will be tougher.
So in PaveHog 1 also, we have actually two different dies and they're modeled separately and then stitched together. And so what could happen around the interposer, let's say we are focusing on the logic die and we need some help with the interposer. Maybe we need some help from Alchip, right, to do this interposer model, right, the prototype interposer, just the VHM region alone, and then give us the model.
Then you have to start that conversation now because they're not even aware of this.
Okay. Okay. So we'll actually prime them then. We are doing the AP memory.
You want to drive that down?
Sure. Yeah. So we actually the first step is to talk to AP memory, get the ball map, bump map, right? Propose from bump map from them, and then we need to do the same prototype, just like we did in PaveHog 1 and 2. It's just extension, it's a simplified model that they do the layout and they give us the model for that. And then Krishna is going to do it on the logic die, that full prototype, and then we stitch them all together.
The problem with the interposer is to be done by the Alchip because
they assume that they will do the project.
Yeah, that is not decided yet.
Okay, we'll talk to APM, and because APM has done is what did this for PaveHog 1,
right?
And if they can do this, whatever you're asking, we are good.
Yeah, I think if you can keep it within APM and us, I think it will be better.
Yeah, sure, yeah. I think it's super because same as PaveHog 1,
we
right?
need to make a decision on the ASIC vendor soon, but you know, it's still not there yet.
I see. So yeah, we'll first talk to AP memory.
Yeah, I mean,
because it's very small question.
Yeah, APM should have that information from PaveHog 1.
Correct. Yeah. So the same technology, same information. Right? We can start there. Yeah.
By the way, is this DRAM die going to be in the same? Which process of TSMC? Is it F25 or F25E?
Well, what I heard is F25. Yeah.
This is what PaveHog 1.
PaveHog 1. And when they do a stacking, then you get more capacity. But basic technology is F25. But anyway, this is going to be custom, right? It's not stacking or anything. It's going to be custom for us.
Yeah.
Yeah. Okay. And okay, another thing, Max, is actually we talked about putting interposer also into the DRAM, right? The DRAM, that option 3, where you have DRAM plus interposer. Interposer is for silicon interposer for the capacitors, right? One is dedicated DRAM, and then they have the DRAM die, but it only used for capacitor as a backup option.
Yeah.
And hopefully that won't change the bump map interface. It's only changing the right. Nothing should change that part. Just want to have kind of alert that we don't want to change any bump map because we added another one. Right?
Is it a better capacitor layer? Capacitor layer, I don't see any routing conditions. That's what my common sense. If you remember C4 case.
So you can like pass through, just like
pass through, and then any connection you like to go, you just go. But it's all.
Yeah, just like in Corsair.
Yes. Yeah.
Okay.
That's my own thing.
So that you were talking about the stitched interposer, right? Like was Jerry okay with that?
And Jerry says now he has so many options. That's why this is one of the options for him. If we end up with a silicon capacitor or silicon whatever capacitor, he's open for now talking about. But thing is, we really need a capacitor, additional capacitor one. That's the first step. We gotta.
No, it's hard to make this call
Yeah.
right now, but we want to be prepared for it.
Yeah, no, because that changes the bump map, right? Because now there won't be.
It won't change. It won't change the bump map, but giving him enough caution that it might come.
So let's say, for example, C4 case, we had the logic die and then C4 and then micro bump and then C4, but bump is 130, 130. So which means silicon interposer is in and out, very, very flexible. It's a 130, I can make it 130 because only capacitor layer plan out. Then I just have a go through or make it horizontal stitching to the coupling capacitor. That's much easier, which means it's very, very flexible. According to my understanding, it's 36 to 130, whatever number I think we do that.
Okay.
So
there was another option, right, where you can have a bigger
interposer
with all the chiplets.
Bigger is more like to me is a stitching for one logic to another logic. That's another one.
Yeah, that's true. But that actually depends on the logic architecture team, right?
Yeah.
Whether they need the higher 2x more bandwidth is a compulsion or not. So
even if that is not required, we will close timing better with that, because then you're only going through the silicon, you're not going through substrate.
No, but the timing won't affect anything because it's currently T2D is designed for organic substrate, like going through this channel.
Oh, right. Will it have to be redesigned if it's?
Yeah, you'll have to redesign. You have to make it smaller. Design will be a change again.
So the same design will not go to the interposer. Maybe
I think so. Maybe Vishal can answer better than
maybe
me.
an over design, but
Over design, not under over design.
Yeah.
No, it's actually density. You are putting 2x more, right? You need to make
No,
sure
let's say
that
we don't want to
density
put 2x more. Right?
but still you want to do this.
Yeah, but just to reduce the losses on B2B, right?
No, it won't. It won't make a big difference because the losses will be higher in silicon interposer.
But that's
Because
of
the loss of the silicon is higher.
Narrow. But shorter. That's
Shorter. You will have to go through different set of challenges. Maybe you may not have same challenges as substrate, but you'll have to go through a different set of challenges. On this.
Okay, so then that's not a.
For me, silicon interposer, larger one, not low stitching, still the one just like our C4, just like another interposer, but sitting on each other, going for the different one. But thing is now the horizontal side gap, which is the 750 now for getting double. Because every single time you go to the share double, then I need the 750 and I need another 750.
Correct. Yeah, you will have to pay that penalty because of it. But I thought you were going to improve find a technology that we're going to reduce it.
Yeah, that's what we are discussing today. Yes.
Okay.
But a couple of ideas, but anyway, I'll talk about it in Thailand.
So will the vertical height increase with the silicon interposer? the cap, silicon cap interposer. The vertical height will
Oh,
increase.
no, it won't. Yeah, that is what he'll actually grind it so that it's actually stack thickness remains the same. So like this is similar to that Girish was proposing that stacked DRAM, right? Exact same technology. Except the DRAM, we put the silicon caps there.
So anyway, I'll come back, but the low bump change, physical footprint is almost the same as what you talk about. That's my topic. Okay. That is the topic for discussion with AEC. Okay.
Oh, interesting. I don't know how they grind it. So it's so small.
How long do you take to make a final course that we need a specific capacitor or additional capacitor or something? How long it take?
No, not like you need the net list and then do the analysis and all that, right? It's usually
You mean on the
about.
You mean on the interposer or?
No, whatever capacitor.
Separate interposer just for silicon cap?
Yeah, just like what we did in course said, if you
So
don't do it.
you'll have a logic die, you'll have a DRAM die, and then a silicon interposer.
Yeah.
Wow, yes, that's but
No, that's not how to make that if you need it, actually how to
but
make that
then,
happen.
Like, I thought the whole idea was this cap needs to be very close to the die. If you have the interposer, if you have the DRAM in between, how effective is
Yeah,
the
but
cap?
DRAM will become thinner in that case. It's grinded so that it becomes thinner. The overall stack thickness remain the same. It's about 100 microns, 50 microns, right? So just like that, they have the memory proposal, right? Stacked memory. So the stack thickness remains the same, but they're back grinded so that it's very thin. The silicon itself is only 10 micron layer, right?
Yeah.
The silicon itself is only 10 micron. Rest of them are mechanical support. The 750 micron.
DRAM is how much?
No, the DRAM silicon, DRAM layer is only 10 microns. And rest of them is actually purely a mechanical support. Right, so they can grind it as grind it so that they can have two dies wafer on wafer bonded.
No.
Yeah. So it's a wow process.
Right.
Okay. So between the DRAM die and the silicon cap interposer, it's a
Then you have after that you have a substrate.
After that we have substrate. So for
I
the
think we shall want to have fun with the extra.
on the D2D. No, that's what if you grind it, if you thickness, the TSV go through it, it should be the same. The parasitic should not increase. We'll have to prove that, but maybe we should, if you're going this way, maybe we should get that model and verify that we don't have a last minute surprise.
Yeah.
Right. I don't think it should be a surprise, but something we'll have to thoroughly verify because the wafer on wafer, we have only 1.4 micron pitch, very thin, right? And we can have a lot of shielding in between grounding so that we'll not have any crosstalk issues.
Do you have any concerns, Vishal, on this?
You see what happens. This reminds me of like double cheeseburger, you know, like like putting stacking.
Yeah. So to give you a timeline, it's not going to be immediate. It's probably a year at least, right? There's 6 months to tape out because we need to get that current profile.
Yeah. That's why
and see and all that. We are trying to
The reason, I mean, let's say we take like 9 months or something to decide, okay, we need the silicon cap. What's the downside?
let's say from my side is I have a here for fire. So fire can accommodate any hidden structures, any silicon step structures. And then once everybody define in the one basic set, and then when I define the second set, then I can accommodate whatever we think we better have as a backup. That's the fire main focus.
Yeah, we should actually keep that up.
You want to actually sort of emulate everything that you can, what we potentially could see on wrapper fire. So if there is an additional whatever the interposer, then you want to add that also.
Because right now, nobody, we are not sure about we need the additional capacitor or not. And we just only talk about it and the logic, and then, but now where to put it, how to put it. And to me, I need just vehicle, and then get a feedback from AEC said, I want to try this way. Because this is the maybe the future directions. Then I could accommodate that between capacity integration scheme, they think is smart. Then hopefully I'll propose you back and they said everybody agree with the ELAN and then silicon wafer on each other by table bonding, the AEC like it, then go for it. ASC may think this is a good solution for everybody and go for it.
Actually, for AAC should get one die, right?
Yeah, one die for them.
So it should not matter to them.
Oh, no, they matter because there's when they have a die, spec above spec, two-way perspective here, and one is in, another is in. They have one test with second test with. So somebody have to make sure this stress propagation doesn't happen from the microbump to the C4. That's why the ASC need to deal with the backside of the C4 reliability, C4 stress. And then, but they also need to worry about the micro.
So then in that case, can we use the APM is developing the stacked DRAM process, right?
Yes.
Can we use that as a
Yes.
starting point? Because we
Yes.
have developed that whole body interposer, right?
Yeah.
So we can use that as a
Yeah,
starting
yeah,
point.
yeah, yeah. That's what I'm saying. I would like to accumulate whatever existing technology from APM, which is a step away. I can just go ahead and use it and plug it.
Exactly.
Yeah.
Okay. So that we can use interest in firewall
Yeah, yeah,
as the backup option.
yeah, yeah.
So instead of stack DRAM, we want to use one,
Yeah.
some dummy kind of thing.
Dummy, yeah, exactly. It's really stacked DRAM, except DRAM we just remove all the circuits and use as a capacitor.
But the likelihood of having us having a silicon cap interposer is pretty high, I would say.
Given what we went through in Corsair, yes, it's high.
Right.
And we'll have to probably implement
I
the
mean,
power
there are some
management.
architectural improvements that we're thinking about, like,
Right.
because the ramp up doesn't happen all at P0.
Correct.
Right? So the-
Staggered.
our time,
Yes.
that should alleviate DI by DP, but in spite of that, like the absolute power itself, right?
Is high.
Right.
Correct.
So then you have some effect of the DI by DP that you get.
Correct. Yeah. So we'll definitely have to plan for a backup solution. Yeah.
I would think that the other way, actually just plan for silicon cap to begin with.
Right. And then remove it if you
Then
don't need
remove
it.
it is easier.
Okay. Yeah. That's a better way to look at it. Yeah. Otherwise, last minute, we'll have to, everything will be scrambled. Yeah.
Because it'll affect D2D for sure, I know, right? It'll affect the other IPs that we're gonna have, PCI and DDR.
Yeah.
So we need to ensure all of that works.
Okay. That's why I think they make micros higher. Then everybody says,
Let's do that. Let's actually plan for the worst case and then we remove it. if
So
we
let's
don't
say
need
we go with that approach, right? What is the downside? Let's say we don't have the silicon cap. What does that mean?
it. No, we will have to deal with TDI very transients, more noise, right? And we may have the Vmin failure. The failure is actually a Vmin. We may not meet the Vmin spec at the transient when all of them switching at the same time. The group, and we'll have group detectors and all this,
Sure.
the instrumented now with Raptor. That will be the problem. Vmin, we have to reduce the frequency,
I
performance, and all
mean, we're
that.
planning for all of that, right? With mobile IPs and all that, we're planning for that, right? In terms of design itself, but like, my question is, let's say, if we go with this approach of adding a silicon cap, but later on we said, okay, we don't need this. What is the downside?
Oh, I don't see any downside.
Nothing.
Because
as
we
far-
plan for the worst
Nothing
case.
as far as signal integrity goes?
No, because we already have the current channel, we know what the characteristics are without the silicon cap. And when we add the silicon cap, we know what it is. It should be same, but we will verify that as well. So we have baseline with the current D2D, PFHawk2 and PFHawk1, we have baseline. Right, and we expect that when we add silicon interpore cap as well, it should be the same, but we'll completely prove that as well. Sorry, Vishal, the question.
no, one question, sorry, what is the frequency response we are talking about on this silicon?
Silicon cap's
What is the
response is pretty high, about 50 to 100 megahertz, or even higher. Right, because
the 50 to 100 megahertz,
hmm.
how is it going to help in the D2D that is actually running at a faster frequency?
No, we actually see most of the high frequency gigahertz and everything are actually contained within the die itself. Right, where we have problem is somewhere between 500 megahertz to 50 megahertz is where we have the trouble. And we can't put the capacitor in the package, it's too far away. We can't put in the die because there's too big capacitors required. And that's where the interposer caps comes in. So in between. Any high frequency in the order of 10 gigahertz is all taken care by whatever caps we put it on the die.
No, that part I understand. What I'm saying is, what is the D2D running at when we are talking about what is the speed at which it's running, right? Because the cap is going to help only in that frequency. So usually runs at 32. And most of the capacities that the DTD relies on will be inside the DTD itself. Okay. So this is more of not a D2D kind of a group, but it's more of something that's happening in the
Digital logic, right? The core digital compute units.
Code is running at 1.5 gigahertz, right?
No, true, but we'll also have a lot of low frequency events as well. See, suddenly what will happen is all clocks will be quiet and everything will come up at the same time. And that's the point you want to address. When all of them switch at the same time, right? That's where we have more trouble. When all of them continuously running at gigahertz range, we don't have problem. All the capacitors inside the die will take care of it. But when you actually stop, we had this case in Corsair when everything becomes quiet, right? They finish the compute, they start the communication, and then start compute again after the communication part. And that's where this was a problem.
And that is in the hundreds of megahertz frequency range?
Yeah, I mean, that is correct. Because because there are a lot of components in that. It's not just one frequency component, the current profile. The current profile has multiple frequency components. And the way we could not solve is really in that 500 megahertz to 50 megahertz current transits.
Okay, so that's where the Z of kind of peaks is, right?
Yeah, exactly. You look at the resonance, yeah, that's where.
Okay.
Yeah, if you have architecturally idea that we can avoid that the current going peak by using loop director and then reducing the frequency at that point, it would help a lot. But that needs to be proven, right? Until then, we'll say we'll have a capacitor.
Yeah.
Right?
Sure. Yeah.
Okay, so anything needs to be done, Max, for that? Let's say if you change the plan to that, we are going to have the capacitor as a default option.
Actually, still the
Same, because we have the same APM technology.
Yeah.
Right. Okay.
Same partner and then just asking different spectral and aspect.
Okay. And the minimum they have is 2 die, right? The minimum that APM offers is 2 die stacking, correct, for the memory?
For the hybrid bonding.
Yeah. Okay, so that's what we will use then for the silicon cap layer.
So what you're saying is that they'll just replace one of them with silicon cap.
Yeah. They don't do any DRAM, the same wafer, same technology, everything. Except instead of putting DRAM circuitry on it, we just use only the capacitor part. Right, it will be a lot simpler for them too.
No, but it's a different way.
So what I know.
Exactly the same because you probably need more cap.
No, it's the same technology, same wafer, everything same. Right, except that we remove that transistor part.
So what I know is this way, let's say almost all memory guys, when they develop the new packaging technology, I say everybody developed their own chip and then develop hybrid bonding technology. I think APM should have not a functional guy. They should have rules of spectral wafer based on page. Otherwise, engineer consume the DRAM wafer a lot. That's not the way.
Right.
So then I can go and take it there one and then you give me the daisy chain structure with the hybrid. Then I can just grind whatever frequency we want and then put it into the file hub. Then I can just stick them together and then okay.
Right.
No,
So I don't have
But for the hybrid bonding, the bump matter is completely different on the bottom, right? Like on the where the hybrid bonding is happening. That is a
no, inner pitch is different. Inner pitch is different, but outer pitch is the same. You can get mixed up.
on the outer, they'll have to go from the inner pitch to the microbumps, right? Like because on the upper part of that 2-layer thing, we have to put microbumps. right? Because on top it's a COW. Right?
Yeah.
Correct, yeah. So
So-
see, let's say if you don't do the silicon interposer, the silicon cap, they only need directly put C4 layer on it. Right now they have to put a micro bump layer and connect. So there will be change involved. It's not like transparent. You will have to.
Why can't you stay with C4 bump on that layer?
No, my hybrid bonding don't work with the C4.
Oh.
Hybrid bonding requires very small pitch, right?
Yeah, and you cannot
1.4
grind down
micron.
to 10 micron with micro.
131.
I learned that from.
Maybe I
Max.
can show that the pattern for everybody on the same page. Maybe I can do the pattern for everybody. And then I can explain why this one is actually comparable, why we don't need to change it, even we change it from A to B, still upper, lower, bump is the same. I will explain why.
So but then we need to make call soon, like if they have to make that micro bump on both sides, right?
Correct, yeah.
Yeah.
It's a change.
It's a change.
Yeah, it's a change. We need to be.
Micro
Yeah,
on
no.
both sides, then
No,
the.
No,
then the
not
height
micro
is-
bump, not both sides. And the hybrid bond, the HB layer on the other side, right? Instead of C4.
I'll say. Okay.
So we need to actually make sure they are aware of this. Hey, we are not directly going to put the C4. C4 is have one more layer down. And you need to plan for this layer. It's actually inserting the extra layer in between. The C4 remains the
We
same.
need, one cartoon showing.
Yeah, that's what I'm saying. I will give one final cartoon and I will explain what the steps and we will go and the process of development step. Once you read it, then you understand what the final steps look
Right,
like.
yeah.
And then you can say that you can take this one, plug in another, that's what also I'm going to do.
Yeah.
A final cartoon.
Sure. Yeah, we should discuss this with AP memory.
Yeah.
So saying, hey, we want this as an option. We want this not as an option. We want to have this.
So then we should like, just prepare the material and send it
Yeah.
to them ahead. So next week.
Yeah, let's go.
Next week meeting we can.
Yeah.
Yeah,
Talk
it's-
through that.
Yeah, I
But
think we should-
otherwise, like, I think like what you're saying is, we won't meet that end of June.
Yeah.
Bump map thing.
Can we say